Another example of solving for the DC analysis. This is example 3 for the voltage divider bias circuit. In the voltage divider bias circuit, we've added a second resistor down here on the base, and these are lower values of resistors which result in a stiffer voltage source that creates the base drive circuit. And this gives us a more consistent operating point even though the betas are different. In the voltage divider bias, most of the current will travel down this way, but a little bit of the current will flow into the base, resulting in a larger current flowing from collector to emitter. The method of solving for the DC analysis is the same as before. We redraw the base drive circuit as a single voltage source and a single resistor, and in order to do that, you have to Thevenize these two resistors. We have two resistors here and one voltage source, and by Thevenizing those out to a single resistor value and a single voltage source, we can now put those values in for the base drive circuit, 4.36 volts and 18.1 K. Once you've got those values in, then we can use KVL to find the base current. So we're going to solve this loop current. As we go around this loop, we see that we've got about 4.36 volts here and 0.7 volts here. That means that there's about 3.6 volts, 4.36 minus 0.7. That's about 3.6 volts, which have to be dropped across these two resistors here. This resistor here, we would use its value directly, but in order to find IB, we need to move this resistor over to the base side and get its equivalent resistance as looked at from the base. And we do that by multiplying it by beta plus 1. So IB, a voltage over a resistance. Which voltage? 4.36 minus 0.7. That's over here. Which resistance? Well, that would be this resistance plus beta plus 1 times this resistance. Put those numbers in, you should come up to 71.1 microamps. Now that we have the base current, we can solve for IC and IE. IC is simply equal to beta times IB, which is 100 times 71.1 microamps, or 77.11 milliamps. IE is a little bit bigger. IE adds in that 1 unit of base current, so it's beta plus 1 times IB, which is equal to 101 times 71.1 microamps, which is 7.18 milliamps. Now that we have all of the currents in the circuit, we can solve for the voltages across the resistors and the voltage across the transistor. We know these currents flowing down here. This is IC and IE, and with those we can figure out the voltage across RC and RE. So the voltage across RC is simply the current through RC times the value of RC, 7.11 milliamps times 1,000 equals 7.11 volts. The voltage across this resistor is IE times RE, which is 7.18 milliamps times 330, which is 2.37 volts. So this has about 7.1 volts across it. This has about 2.4 volts across it. We started at 18. The rest of it has to be across the transistor. So to solve for VCE, we take the 18 volt supply voltage and we subtract the 2 voltages across the resistors, and that leaves us with VCE. So that would be 18 minus 7.11 minus 2.37, and that comes out to 8.52 volts. Now we've got all the values we need to plot an operating point on this graph. We've got the VCE and we've got the IC. But first we need to draw the load line on the graph from IC sat to VCE off. So to find IC sat, what we do is we short this transistor. We think of it as a short and figure out how much current would flow from the supply voltage down to ground. So IC sat would be VCC divided by the total resistance in that path, which would be 18 over 1330, which is 13.53 milliamps. That's IC sat. VCE cutoff is the voltage that we would see across the transistor if it was completely off. And how you can solve that is you can imagine that you pull the transistor out of the circuit and you simply figure out what's the voltage on the terminals that are left behind. If there's no current flowing through this guy, there'll be no voltage across him, so VE will be 0. If there's no current flowing down this way, then the collector will be at the same voltage as the supply voltage, so this will be 18, this will be 0, VCE off would be 18 volts equal to the supply voltage. Now we plot that on a graph on the horizontal axis, which is volts across the transistor. Here's the cutoff voltage at 18 volts, so this would be one end of our load line. On the vertical axis, this would be current through the resistor, or through the transistor. And that would be 13.53 milliamps, so we put a point out there. Draw a dead straight line between those 2 points, and then we can plot our final operating point in the middle of the load line.